late. The rest of the house is quiet. And you are staring at the cool blue tint of your IDE, just trying to figure out why your brilliantly coded AI agent acts like it has total amnesia every time you restart your dev server.
Yeah, the classic amnesia problem. It's so frustrating.
Right. I mean, you've given it tools, you've given it reasoning loops, you've engineered the perfect prompt, but it still can't remember the specifics of the proprietary code base you literally just fed it 5 minutes ago.
Exactly.
So tonight, we are fixing that amnesia. We are doing a deep dive into the foundational architecture of retrieval augmented generation, or RAG. Because honestly, if you want to build autonomous systems that actually scale, you have to stop treating an LLM like a magic 8-ball and start giving it a persistent memory.
And that amnesia, it really is the single biggest bottleneck when you're moving an AI app from a neat local demo to a real production-grade system.
Oh, for sure. The demo always looks flawless.
Right, because a language model natively has incredible general reasoning capabilities, but its context window is fundamentally ephemeral. And, limited in size. You can't just stuff a million-line enterprise code base into the prompt every single time a user asks a question.
Or like 10 years of customer support tickets. You'd blow through your token limits in 2 seconds.
Exactly. You need a way to store that vast amount of unstructured data and, more importantly, retrieve only the incredibly specific slices of it that matter at any given microsecond.
Which means we basically have to completely rewire how we think about databases. Because most software engineers, we cut our teeth on relational databases.
Postgres, MySQL, all of that.
Yeah. We are trained to think in terms of tables, rows, primary keys, and these strict schemas. We write SQL queries with absolute certainty. Like, you query a database for a user ID, you either get the row or you get a null return.
It's binary.
Right. But human language doesn't work like a primary key. Human meaning is messy. Trying to query for meaning using a where clause is it's impossible.
It really requires a total paradigm shift. You're moving from categorical storage to continuous semantic storage. So instead of storing data in neat relational tables, we are utilizing vector databases.
The vector databases.
Oh.
The buzzword of the decade.
Yeah, but for good reason. These systems, they don't store text as human-readable strings for keyword matching. They store text as high-dimensional vectors. And a vector, at its core, is literally just an array of floating-point numbers.
Just a massive list of decimals.
Exactly. But what those numbers represent is a coordinate in a highly complex mathematical space.
Okay, let's ground this for a second, because high-dimensional mathematical space sounds like theoretical physics.
Yeah.
But practically, we were talking about passing a piece of text, say, a paragraph of documentation, through an embedding model, right?
Correct. The embedding model is the translator.
Right, and that model analyzes the text and spits out this array of numbers. I think some of the common models output, 1,536 numbers?
Yeah, the standard OpenAI embeddings use 1,536 dimensions.
So we are plotting this paragraph in a space with 1,536 axes. What I want to know is, what do those axes actually represent? Are they specific grammatical rules? Like, is axis number 4 the concept of verbs?
Well, no. Not in a way a human would neatly categorize. It's way more abstract than that. The embedding model, which is usually a transformer-based neural network, it determines what those dimensions represent entirely on its own during the training phase.
Oh, so it just figures it out by reading.
Yeah, it reads billions of parameters of human text and learns the statistical co-occurrence of concepts. So one dimension might loosely correlate with the concept of royalty, another with gender, another with plurality.
Okay, that makes sense.
But hundreds of others capture incredibly subtle subtextual relationships that we don't even have words for. So when you pass a paragraph into the model, it activates across all these learned dimensions, generating a unique coordinate that represents the exact semantic weight of that text.
Wow, so we are essentially mapping language into pure geometry.
That's a great way to put it.
And the brilliant part of this geometry is that physical proximity in this vector space corresponds directly to similarity in meaning.
Yes, proximity is meaning.
So if you plot the vector for the concept of canine health, and then plot another vector for a document about sick dogs, those two coordinates are going to sit extremely close to each other in that 1,536 dimensional space, even if they share literally 0 overlapping keywords.
Exactly, because the machine doesn't know what a dog is. It has no concept of a physical animal, but it mathematically understands the topology of the language surrounding dogs.
Which is wild to think about.
It is, and this is exactly what unlocks semantic search. In a traditional database, querying canine against a document containing only dog yields 0 results. Unless you manually maintain, like, an exhaustive synonym table.
Which is a nightmare to maintain.
Total nightmare. But in a vector database, the model already mapped their relationship. It knows they live in the same neighborhood.
You know, it makes me think of organizing a massive million-book library, but totally abandoning the Dewey Decimal System. You aren't organizing by author or publication date. You are organizing purely by the exact vibe and conceptual theme of the book.
Oh, I like that analogy.
Right. So a hard sci-fi novel about interstellar politics doesn't just get dumped in some generic fiction wing. It gets placed at an exact physical coordinate, sitting exactly halfway between a densely technical astrophysics textbook and a political thriller.
Yeah, exactly.
So if I ask for a book about political maneuvering in low gravity, the system just walks to that specific coordinate and grabs whatever is sitting nearby.
That spatial mapping is the entire foundation of our guy. But, placing the books on the shelf is only half the problem. The retrieval part requires us to actually calculate the distance between your query's coordinate and the coordinates of all those books.
Right, because we need a mathematical way to figure out how close those points actually are.
Yeah, we need to mathematically quantify that gap.
Wow.
If you have a query vector and a document vector, you have to measure the distance between them.
So let's talk about that measurement, because there are a few ways to measure distance in geometry. I think the most intuitive is Euclidean distance, which is basically just taking a ruler and measuring the straight line distance between point A and point B.
Just a straight shot.
Yeah. But in the architecture of modern vector search, Euclidean distance is rarely the default, right? The industry standard is cosine similarity.
Yeah, almost universally.
So why do we throw out the ruler and use angles instead?
Well, Euclidean distance has a massive vulnerability when you're dealing with unstructured text. It is heavily influenced by the magnitude or the length of the vector.
Okay, magnitude. Walk me through that.
Sure. The magnitude of a text vector generally correlates with the amount of text being embedded. So a 10-page technical white paper on machine learning will generate a vector with a much larger magnitude than a single-sentence tweet about that exact same machine learning concept.
Because there's just more text pushing it further out.
Right. So if you use Euclidean distance, the math looks at the physical endpoints of those two vectors. Because the white paper's vector is so much longer, its endpoint is very far away from the tweet's endpoint.
Even though they're discussing the exact same topic.
Exactly. Euclidean math would conclude they are completely unrelated.
Wait, let me push back on that for a second. Because ignoring magnitude feels like throwing away really valuable data. Wait, so if I have a massive 10-page white paper on machine learning and a tiny one-sentence tweet about the exact same topic, their magnitudes are completely different. But cosine similarity knows they are pointing in the exact same direction.
Yes, it isolates the direction.
But doesn't a 10-page white paper inherently contain more nuance and detail than a tweet? If we just ignore the length of the vector, aren't we losing the distinction between a really deep dive document and just a passing thought?
We are losing that specific distinction, yeah. But for the purpose of retrieval, that is a feature, not a bug.
Really? How so?
When a user queries your agent for information on machine learning, they want relevant topics regardless of format. Cosine similarity solves this by measuring the cosine of the angle between the two vectors, originating from 0. It purely evaluates directional alignment.
Oh, okay. So
Yeah.
it's all about the angle.
Right. The white paper is a very long line pointing in the machine learning direction. The tweet is a very short line pointing in that exact same direction. The angle between them is practically 0.
Ah, I see.
So cosine similarity registers this as a near-perfect semantic match. It completely abstracts away the document length and isolates the core topic.
Okay, that makes a lot of sense for a search application. You just want to retrieve the concept, and I guess you can filter by document type or length later in the application logic if you really need to.
Exactly. You handle that at the application layer.
But relying on directional alignment introduces a terrifying compute problem. I mean, if I have a database with 10 million embedded documents and a user submits a prompt, my application embeds that prompt into a query vector. To find the closest match using cosine similarity, the system has to calculate the angle between my query vector and every single one of those 10 million vectors.
Yes. Traditionally, it is an ON linear search. It's often called k-nearest neighbors, or KNN. You are literally doing floating point math across 1,536 dimensions 10 million times for a single user query.
That compute cost is astronomical. And the latency I mean, you'd be sitting there watching a loading spinner for minutes.
Mhm.
Production AI agent needs to retrieve context in milliseconds to
Mhm.
actually feel responsive.
Yeah.
You can't perform a brute force calculation across the entire data set every time a user hits enter.
You can't. Which necessitates a compromise. To achieve sub-millisecond latency, we abandon the guarantee of finding the absolute perfect match, and instead aim for an approximate perfect match.
So we're cheating the math a little bit.
A little bit, yeah. We move from KNN to ANN, approximate nearest neighbors, and the dominant algorithm powering almost every major vector database today is HNSW.
HNSW, Hierarchical Navigable Small World.
That's the one.
The engineering benchmarks for HNSW are ridiculous. It routinely achieves, 95 to 99% recall accuracy while examining less than 1% of the database.
Yeah, it's incredibly efficient.
But skipping 99% of your data to find a match sounds incredibly reckless. How do you mathematically guarantee you aren't ignoring the exact document the user desperately needs?
Well, you don't guarantee it. That's why it's called approximate. But you make it statistically highly probable by building a highly optimized graph structure during the data insertion phase.
Okay, so it's all about how you organize it up front.
Right. HNSW doesn't just dump vectors into a flat list, it constructs a multi-layer graph. Think of it like a global transportation network. The top layer of the graph only contains a few highly connected nodes, like major international airport hubs.
Okay, so just the big entry points.
Exactly. Then the layer below that has more nodes, like regional airports. This continues down through multiple layers until you hit the bottom layer, which contains every single vector in your database, densely connected to its immediate neighbors.
Oh, wow. Okay, so if I query the database for a specific piece of log data, the algorithm doesn't start at the bottom layer looking at every single log. It enters at the top layer.
Yeah.
It lands at a random major hub. It calculates the cosine similarity to the few other hubs at that top layer, finds the one pointing closest to the direction of my query, and just hops to it.
You got it. Then it drops down a layer, it evaluates the regional nodes connected to that hub, finds the closest one, hops, and drops down again. It's a greedy routing algorithm.
That's brilliant.
By the time it hits the bottom, densely packed layer, it is already standing in the correct semantic neighborhood. So it only evaluates the local neighbors in that specific cluster to find the closest match. It mathematically ruled out those entire other regions of the graph during the high-level hops.
It's like zooming in on a digital map. You don't scan every house on Earth to find a coffee shop in Seattle. You click the U.S., which is the coarse layer, then Washington State, then Seattle, then the exact street, the fine layer. You skipped 99% of the map, but still found exactly what you needed.
That is a perfect analogy, and doing that drops the search complexity from linear to logarithmic.
Incredible. But there has to be a catch.
There is. The trade-off is memory overhead. Storing all those graph layers and pointers takes up significant RAM compared to just a flat index. But for a software engineer building RAG, trading RAM for millisecond search latency is a deal you make every single time.
Every time. Okay, so now that we have the theory of storing meaning and the algorithm to search it in milliseconds, let's pivot to the practical implementation. How do engineers actually implement this in the real world tonight?
Well, this is where a lot of people stumble.
Right, because a developer could hear all this, spin up a dense vector index, deploy it, and then watch their AI agent completely fail at answering basic user questions.
Exactly, because dense vector search has a massive, fatal blind spot.
And what is that?
It struggles immensely with exact keyword matching, out-of-vocabulary terms, and highly specific identifiers. Dense embeddings are trained to compress language into semantic meaning. But sometimes, there is no underlying meaning to compress.
Ah, I see where you're going with this.
Think about it. A user querying an agent for an exact error code, like error 504, they don't want documents conceptually related to network latency or server disconnects. They want the specific log file containing that exact string.
But the embedding model looks at error 504 and tries to be too smart. It maps it to the general neighborhood of connection failures. So when it searches, it retrieves 10 documents about packet loss that don't contain the error code at all.
Exactly. It hallucinated relevance because it prioritized concept over literal syntax.
Wait. This is the ultimate reality check for developers. We literally just spent all this time talking about the magic of multidimensional meaning, but at the end of the day, you still can't throw away your old school keyword search. You literally need both to build a bulletproof app.
You absolutely need both. This is why relying purely on dense vector search for RAG is a rookie mistake. The industry consensus for robust retrieval is hybrid search.
Hybrid search.
Yeah. You run your dense semantic vector search in parallel with the sparse vector search. And sparse vector search usually means implementing the classic keyword scoring algorithm, BM25.
BM25. That is the engine that powered traditional search for decades before embeddings even existed.
Yeah.
It operates on a completely different mathematical foundation, right? TF-IDF, or term frequency inverse document frequency.
Yep, that's the one.
So how does that offset the weaknesses of our semantic geometry?
Well, it looks purely at the presence and rarity of specific tokens. Term frequency counts how many times the exact word appears in a document. Inverse document frequency looks at how common that word is across your entire database, and it penalizes it if it's too common.
Okay, so if I search for the word the, it might have a high term frequency, but it appears in every document, so the IDF severely penalizes its score.
Exactly, but an exact error code. That appears frequently in a few specific logs, but rarely across the whole database. So BM25 will assign that log an incredibly high relevance score.
Okay, so hybrid search runs the HNSW semantic search to find conceptually aligned documents, and simultaneously runs the BM25 sparse search to find exact literal matches.
In parallel, yeah.
But how do you combine those two completely different scoring metrics? I mean, a cosine similarity score of 0.89 and a BM25 score of 45.2 are apples and oranges. You can't just add them together.
No, you can't. You have to normalize and fuse them. The most common technique for this is reciprocal rank fusion, or RRF.
Reciprocal rank fusion, how does that work?
Instead of looking at the raw scores, RRF looks at the rank of the documents in each individual search result. So if document A ranks first in the semantic search and 58th in the keyword search, its RRF score is calculated based on those rank positions.
Oh, I get it.
Yeah, so if document B ranks 5th in semantic and 3rd in keyword, it might actually beat document A overall because it performed strongly across both paradigms.
That's super clever.
And you can also apply alpha scaling, where a developer manually assigns weights, say, 70% semantic, 30% keyword, depending on the specific use case of their agent.
This is exactly the pragmatism you need to build bulletproof systems. You don't abandon the old-school keyword index, you just layer the multidimensional semantic space right on top of it.
Best of both worlds.
Okay, let's talk infrastructure. For the dev listening right now who needs to implement a vector database before morning, deciding where to host this memory is the next big hurdle. The vector DB landscape is super crowded, but we can look at it across a spectrum of deployment strategies. So let's start with the fully managed route.
Pinecone. Yeah, they really popularized this serverless vector database model. It is pure software as a service. You don't provision compute, you don't manage memory limits, and you don't even configure the HNSW graph parameters unless you really want to.
Just plug and play.
Pretty much. You authenticate with an API key, send them your vectors via an HTTP request, and they manage all the storage and the retrieval.
The developer experience there is incredibly frictionless. But the trade-off is architecture dependency and network latency. I mean, every time your agent needs to think, it has to make a round-trip network call out to the public internet to hit Pinecone servers.
Yeah, that latency is a real factor.
If you are building an agent that runs hundreds of reasoning loops a minute, that network latency adds up really fast. Not to mention, sending proprietary enterprise data out to a third-party managed service is often just a non-starter for strict compliance environments.
Exactly, which pushes a lot of engineers toward local, lightweight options, especially during development and prototyping. And the standout here is Chroma.
Chroma. I've heard a lot of good things.
It's great. It is designed to be deeply embedded directly into your application. You install it via your package manager, and it runs in memory or persists to your local disk.
It gives me strong SQLite vibes.
Yeah.
It just gets completely out of your way. You don't have to spin up Docker containers or manage a separate database server. It just runs inside your Python process.
That's the beauty of it.
But I assume running an in-memory database hits a hard wall when you try to scale from thousands of documents to hundreds of millions.
Yeah, Chroma is fantastic, but it is not designed to be a highly available distributed cluster for massive enterprise workloads. When you hit that scale, when you have billions of vectors, constant high-throughput ingestion, and strict uptime requirements, you need dedicated infrastructure.
And that is where a solution like Milvus comes into play. Milvus is heavy artillery.
It really is. It is an open source, cloud native vector database built specifically to run on Kubernetes. It separates storage from compute, allowing you to scale your query nodes independently from your data ingestion nodes.
So it's super resilient.
It's highly resilient, but the operational complexity is massive. You don't just pip install Milvus, you need a dedicated DevOps infrastructure to manage it.
Okay, so to summarize the landscape, if you want zero operational overhead, you use Pinecone.
Oh,
If you want a local self-contained development sandbox, you use Chroma. And if you are operating a massive enterprise microservices architecture with a dedicated ops team, you deploy Milvus.
that's the perfect breakdown. But regardless of the infrastructure choice, the core mechanics remain the exact same. You are still embedding text into arrays, navigating an HNSW graph, and hopefully fusing the results with BM25 to counteract semantic hallucination.
It's incredible to see the full stack come together like this.
Mm-hmm.
We've taken the abstract concept of human meaning and systematically reduced it to floating point numbers. We've measured the angles between ideas using cosine similarity. We've cheated the bounds of computational limits by navigating small world network layers to find matches in milliseconds. And we've brought it all back down to earth with hybrid keyword fusion.
You've officially given your system the architecture to retain and recall context. The amnesia problem is solved. The foundation for an autonomous agent is set.
But memory is only useful if you actually know how to act on it. Having an encyclopedic database of knowledge doesn't automatically mean the agent knows how to solve a problem. It really sets the stage for our next deep dive, transitioning from memory to reasoning.
Right, because now that the AI has memory, we need to understand how it uses it.
Exactly. How do these agents take a complex, ambiguous user goal, query this massive vector space, and decompose the results into a structured sequence of actionable steps?
Planning and task decomposition, that is where the actual intelligence of an agentic system truly emerges.
It's going to be fascinating.
Yeah.
But before we tackle that, I want to leave you with a final thought as you turn back to your IDE. We just spent this entire time dissecting how to map human meaning into 1,536-dimensional math. And it is an elegant, highly functional statistical trick.
It really is.
But if all of our language, our intent, and our context are being reduced to directional vectors, what is falling into the blank spaces between those axes? Think about sarcasm. Think about deep emotional subtext. Think about a deliberately placed pause in a conversation.
Oh, wow, that's a deep question.
Are those profoundly nuanced human elements being successfully mapped by the neural network? Or are they simply being lost in the mathematical void because they don't map neatly onto a mathematical graph?
It makes you wonder if we are actually capturing meaning or just the shadow of meaning that mathematics is capable of measuring.
Something to ponder while you run your next build. Thank you for tuning in late to build the future with us. Keep coding, keep questioning the architecture, and we will catch you on the next deep dive. Have a great night.